Because this is not
okay. So let's see where we left off yesterday. So yesterday, the main punchline was this generalized Adams dichotomy. By Takudrov and I, which is in the measured class preserving setting. So you have an equivalence relation E that's treeable, and the tree we fix a particular tree T. Then we characterize when it is amenable. So this equivalence relation is amenable if and only if it has at most two non-vanishing ends. Also, there was this other condition, if and only if there are at most two ends with infinite geodesics. And we also, it is a dichotomy, so we also, on the other half of the space, we say that we get that E is nowhere amenable, and on that part, that corresponds to having perfectly many non-vanishing ends, which means having a non-empty closed set with no isolated points. And there is also a similar condition with geodesics, but it's only a G delta set. We don't know if it's open, so I posed it as an open question. Okay, so today I'm going to aim to describe the proof of this first in the PMP case due to Adams, just only part A and only with this non-vanishing. So in the PMP case, it's just less than or equal to two ends, right? So I will first describe the proof of that, and then I will tell you what kind of things we did to get it in the measure class preserving setting. So it will involve some sort of abstract lemma, a ping pong style lemma that we call pedalball, because the picture looks like someone is playing the pedalball. So I'll describe that lemma. Basically, my goal is to get to that lemma, because you probably won't care about the rest after the talks, and that one maybe will stay. Okay, so in order to prove Adams's theorem without cost, so this where is it? Like in the previous lecture here, that in a PMP tree is amenable if and only if it has less than or equal to two ends in each connected component. I need the notion of end selection. So this is the proof of Adams's theorem without cost, and that's what I'm going to do first. So end selection, I mean, if you know it, well, then you'll be bored. If you don't know it, it's a very good tool to learn. So it's no loss. So okay, so let E be nowhere smooth. So I'm going to assume this non-triviality assumption. Nowhere smooth, treeable, measure class preserving C bar on X mu, and let T be a string of it. So this is throughout the section. Now I want to define end. So what is an end selection? So for a sub-equivalence relation, Borel, if I don't write, so Borel invariant, an F invariant end selection is a map from X to the finite subsets of, I ran out of place, of course, so of ends of T. So this is the space of ends of T, such that mapping each X in X to a finite subset, to finite set, let's say Cx of ends in the T-connected component, ends in the T-connected component of X. X, so let's look at it for a moment. So each T component contains several F equivalence classes. And each equivalence class chooses finitely many ends in that tree. Okay, that's what happens. Now, where does the Borel come in? I should have said, but I'll say it now. The space of ends is not standard Borel because it is obtained by quotienting out with this end equivalence relation. And this end equivalence relation is not smooth. So the quotients are not standard Borel spaces. However, the space of rays is Borel. It's a Borel subset of x to the n, x to the natural numbers. It's just sequences of x that satisfy something or other. That's a Borel subset. See, someone was asking where Luzin-Novikov was hidden. Here, Luzin-Novikov was hidden. Okay, so now to make this map Borel, I just say that it lifts to a Borel maps on the rays. So in reality, each point chooses it chooses finitely many rays. So different points in the same F class can choose different rays, but these rays correspond to the same end. In that sense, it's F invariant, but the choice of rays isn't F invariant. Okay, so such that it's lift, the lift of this map to, instead of finite set of ends, to the finite set of rays. By x takes, so instead of mapping to this set of ends, I will map to rays starting from x going to that end. This is my notation for it. So let's say eta, where eta belongs to this E, is Borel. Where, so here by here and later by this notation. Oh, I forgot to put t here to mean the ray through t. By x comma eta for eta and end. So by this interval from a point x to an end, I just mean the corresponding ray, unique ray in the tree that corresponds to this end. So by this we mean the ray starting from x, the t ray starting from x, x representing the end eta. Okay, so this is what an end selection is. And so the theorem is that once if f is amenable, if and only if such an end selection exists.
You think about to be invariant.
Oh, I didn't say F invariant map is, and thank you, Ronnie, that's the most important condition here. It's well, I'll put it in red, how about F invariant map from X to, so for different points in the same F class, choose the same ends, select the same ends. Okay. All right, so now the theorem, which I think is due to Adams and Lyons, but is also rewritten maybe in our terminology in JKL. JKL is this most useful survey that has been serving from like 90s for C-bears. So JKL is Jackson, Caprice, Lubov, or 2000, I guess. Jackson, Caprice, well. So the theorem says that, so for basically F is amenable. Suppose E is nowhere smooth. Maybe I already assumed that. Yeah. So with assumptions as above, with the above assumptions, F is amenable if and only if it admits an F invariant Borel end selection in fact, you can make it so because of, so you can make it that instead of just finitely many ends, you know that it has to be 1 or 2 ends unless some parts of f is smooth. So if modulo smooth part, it actually admits less than or equal to 2 ends, and on the smooth part you can do whatever. So you can make it admit 1 or 2 ends. So selection of less than or equal to 2 ends. So if f is nowhere smooth itself, if f itself is nowhere smooth, then this selection, there is a maximal such selection. And it's unique. Oh, it admits, yeah, and it's unique. So there is a maximal selection of 1 or 2 ends, and it's unique up to null sets. Okay, yeah, unique up to null sets. Okay, so each class chooses 1 or 2 ends, and it can't choose more ends. Like this is it. If it chooses 1 end, it can't choose 2. There is no selection of 2 ends for the same class. Okay, up to like almost surely any 2 maximal end selections would, or any other end selection would be a subset of this one. Okay, so but that's what I mean by maximal. And so when I usually talk about end selection, I only talk about maximal. Basically, if you could select, if you only selected 1 end, but you could have selected the second end, then I do select the second end. Okay, so all possible ends are selected, but it's always either 1 or 2. If f is non-smooth, which is we will typically assume, because who cares about smooth? Like smooth are trivial, so we don't care about that. Okay, so with this theorem in mind, I'm going to now try to prove. So now let's prove Adam's dichotomy, or like Adam's theorem, as Martin corrects. Let's prove Adam's theorem, which I'll just copy paste from the first lecture. This once again, this theorem has a very easy proof with cost, but I didn't introduce cost. So, and also cost doesn't work in the MCP settings. Proof sketch is too ambitious to call a proof. Okay, so what are we going to do? First of all, so this direction is easy. So if we assume that if the tree itself, tree T, I guess I want to squeeze T here. So if the tree has at most 1 or 2 ends in each component, then guess which ends I will choose. To prove that it's amenable, I only have to show that there is an end selection of 1 or 2 ends. And yeah, I mean, if it has only 1 or 2 ends, there you go. Yeah, I select it. So just select all ends in each component. All less than or equal to 2 ends in each T component. So T is amenable. So T is, by T I mean its equivalence relation is amenable. Okay, now let's do the interesting direction. So the interesting direction is you assume it's amenable and you want to show it actually has at most 2 ends. So we start with end selection as a black box. So I know it's amenable, therefore I know it admits a selection of at most 2 ends. And then the hope is to prove that the other ends don't exist. There are no other ends. Okay, so let well x mapping to ex be maximal end selection. Maximal E here is the equivalence relation produced by this T. So this is the connectedness equivalence relation of T. So let this be a maximal E invariant and Borel end selection. F selection for T or from T. Now, some classes, some F classes select some T components or E classes select one end, and some E classes select two ends. That means I can split the space into two Borel sets. On one, all of them selected one end, and on the other, all of them selected two ends. So without loss of generality, I can consider the two cases separately. Without loss of generality, it's enough to consider the following cases. The following two cases. Case one, maybe I'll copy. We'll start with case two because that's the easy to case. So okay, I have a picture here which I want. Okay, so this is case two. I number the cases in terms of how many ends they chose. So case two is two ends are selected by each F class. So because there are two ends, you can always draw a sort of ray or not ray, a line, geodesic line between these two. So take a ray that goes to one, take a ray that goes to the other, they merge at some point, so remove this singly thing and you get a line. So let fix for each F class, for each, well, there is no F, sorry, E. For each E class, C, let L be the line, T line, between the two selected ends. The two selected ends. So here is the picture. This end is selected. This end is selected. Now, so we have a line, and it's, you know, you can see it in a Borel way because you see both of the ends. Okay, so this line is uniquely defined. Now, all we need to show is that these bushes growing out of it don't have ends at all. But what happens is that these bushes, like this, basically open sets or sides of the line. You can define an equivalence relation of being on the same side of the line. This equivalence relation is smooth because it has a winner point. Each of the classes have the closest point to the line. That's a winner point, so that's a selector. You know, we violate the first commandment of selecting the point, so it's smooth. But I showed last time in last lecture, let me go back, that, oh, it was an exercise, I didn't show it, that smooth is the same as every class is cocycle finite. In PMP, that just means finite. In non-PMP, it still means cocycle finite. So it's okay. So let's write this down. So the sides of L. So I'll write it in red because I drew it in red. The sides of L are W finite. Even though I'm assuming PMP, I want to keep W, okay? Okay, one.
Left or right is when you remove an edge connected component.
Yeah, it's a connected component. Side is a connected component. Side is a connected component. Hey, it's a good terminology.
After removing this line.
Yeah, after removing this line, you get some bush connected components, and each connected component I call a side, just like when I defined ends and there was this debate. Okay, so the sides of the line are W finite, which being, so I will write in parentheses, being the classes of smooth Z-bear.
Infinite.
Yes, but I want to then use this case later. Okay, I don't want to write it. This is the exercise you didn't do, which is exercise number 3 yesterday. That an equivalence relation is smooth even only if almost every class is W finite. So in PMP, it would just be an equivalence relation is smooth if and only if each class is finite. So this.
Which equivalence relation are you
using this exercise too.
The other another equivalence relation, a new equivalence relation of being on the same side of the line, on the same connected component after removing the line. It's a new equivalence relation. Let's call it F. Being the classes of a smooth C-bar F of being on the same side of the line. Let me write it for clarity. Of being on the same side of the line, and use exercise 3. Okay, thus in PMP it's W finite. Thus in PMP, well, if E is PMP, each side is finite. I want to say comma, and even in M, so it has no ends. So it has no ends, and in more generally in measure class preserving setting, each side has no, all ends of the sides are vanishing, because in fact the whole thing is sum of them. So it goes like everything goes to 0. There's like a maximal element. You know, like all ends in the sides are strongly vanishing, so are vanishing. So this proof, the proof of this case, so it has only 2 ends, this selected ends, done. If this proof works, this case works for the, as I said, for the MCP setting, so I don't have to repeat it later when I do the proof. This one is fine. It's the case of selecting one end that is not fine. So let me copy that picture as well. Whatever, I will copy a bit more of the text, sorry. Now, the other case is when each class selects exactly one end. So one end is selected, one end is selected by each E class, and we denote that end by C plus. So this is C plus X. It's E invariant, so it doesn't matter which X I write here. I could have written this. Okay. So now in that case, we can always define a function of going closer to the end. Like the function takes X to the next point in the, to the next point in the ray from X to that end. Okay, so there's a function, and thus the 3t is just the graph of that function. So thus t is just the undirected version of the graph of the function. Or version of the graph of f. Okay, all right. So now t and graph of f are the same things for me at this point. This is f. Okay, so now what we want to do? So we want to show that the f backends you understand what backends is, right? Like these guys. This is the forward end by f, and then everyone else is a backend. So f backends don't exist. So there are no, in other words, f is one end. That's what we want to show. Okay, so in the PMP setting, so any ideas how to do this in the PMP setting without cost? So like let's say there was a backend. What's wrong with that? So PMP means you can do mass transport without any tilting. With the cocycle, right? So all points have mass 1, all right? So we will violate mass transport by sending the mass of X behind it to all of its preimages. So each point x is going to give mass 1 to all of its preimages. The mass, so how much mass does each x receive? Just 1. It has 1 forward image, so it's received just 1. But it potentially gives more. And in fact, it will give more because this f is cannot be two-ended. If it only gave 1 all the time, then f would be two-ended, essentially two-ended. And then we would have selected 2 ends instead of 1. But I said we selected 1. So because we selected 1 end, okay, I'll say this. So do a mass transport by letting each x in x give its mass, its whole mass 1, whole mass 1 as 1 to each of each preimages. Its preimages. This I'm going to write in red because this is where we use PNP. So each x receives, so each x gives bigger than or equal to 1 and receives less than or equal to 1 by PNP, because there is only one forward image, f image of x. And by PNP, it's still mass 1. There is no relative of, in non-PNP, this other point can be million, weight million, and it would give million to x. Yes.
How can it do less?
It can be less, so then it gives less. Oh, because maybe this point decided instead of giving it to x, gave it to this guy. Oh no, right, it's always 1. Sorry, you're right. 1. Receives 1. Okay, this is the PMP. Okay, so because we selected only one end, f cannot be essentially two-ended. So there are x's, there are points in each f class or orbit or t class, e class. There are points in each e class that have bigger than or equal to 2, bigger than or equal to 2 preimages. This shows that
this looks wrong. I mean, there are points which have no preimages.
Right, you have to shave them. I wanted to sweep them under the rug.
I mean, the integral doesn't add up.
No, basically, no. What I'm saying, if you shave and you're left with nothing, then you were one-ended. And if you shave and you're left with many, you can't be left after shaving these points. You can't be left with 2 ends only, because that will violate the end selection.
It's not true that every x gives mass at least 1, because it may have no preimages.
With a caveat that gives mass. Okay, so you want me to write the caveat? I will write. So this is after Cantor-Bendixson shaving. This is after shaving the leaves. Iteratively shaving the leaves. Yeah, thank you for not letting me sweep this under the rug. Shaving the leaves. Okay, so this shows two less than or equal to 1 by mass transport. Or a contradiction. Okay. So yeah.
If you don't want to do the shaving, you could say you give a pre-image that has an infinite ray that direction. And then
yeah.
say if either there is a ray or there is no, and
yeah, that's equivalent. That's right. Yeah. So then if you don't give anything, then there are no infinite rays in any direction, and if you give, yeah, good sake, thank you. Okay, so so this mass transport thing works. What doesn't work now we would want to get rid of this and get rid of this equal 1. So we need to cook up a different mass transport, which actually we do, me and Robin, but it's super complicated. You don't just do like your pre-images. You have to find some V looking shapes, and then with these V shapes, like anyway. So and these V shapes would prove the unsummability of geodesics or summability of geodesics as well. But this is not the direction I want to go. It's too technical for a lecture. What I will do is prove only the fact that the backends are non-vanishing. So we will now show how to make case 1 work to prove case 1 in the measure class preserving setting. So like the proof of MCP case 1. So again, we have this function f. Maybe I'll copy paste it here again for so again we have this function f, and now we want to show that we need to show that the f backends are vanishing. So to show this, after some a little bit of technical analysis, it turns out the core lemma to show is something in this direction. Namely, we want to show that there are x's that dominate the entire back orbit. Meaning there are x's whose Redon-Nikodym cocycle dominates the entire back orbit. This is sort of the beginning of showing that the backends are vanishing, and but that beginning is like the key to proving it. Like basically, the rest is maybe an exercise with the star, but this maybe is not an exercise. So okay, so a technical analysis shows that analysis boils this down to proving the following key lemma. So I guess core lemma. So I want to show that for almost every x, for almost every E class has points x such that for every y in the back orbit of x in the f back, let's say for every y behind x, and I'll define what this is behind x. So i.e. what I mean behind x, I mean that y belongs to the back orbit of x. So it's just the iterative pre-images of f under f. Okay, so for every y behind x, and I mean that this is bigger than or equal to 1. So for every y behind x, the weight of x, the w cocycle weight of x, is bigger than strictly bigger than the weight of y. And you can say, but you usually write a letter here. For this relation to hold, it will hold with any letter, any point from the class I pick, because it just multiplies. Different points will multiply by a constant, so the inequality won't change. That's why I really think of this as a weight function, and I recommend doing so. Okay, so this is what I want to prove. This core lemma is enough to prove this core lemma, and we focus on that. So we now prove the core lemma. We now
Strictly greater, or
yes, strictly greater. That's what we end up proving.
as you exclude the PMP case, I guess, this argument.
No, you have leaves in the PMP case. So in the PMP case, you would just have no points there, and it would be vacuously true. In the PMP case, you will have leaves necessarily, and leaves have no one behind them, so this would be true. Okay, so this is the non-PMP way of saying, like, we really think of these as somehow leaves, but even though they're not leaves. Okay, so we now prove the core lemma. Supposed to avoid the contradiction, suppose otherwise. Then without loss of generality. So otherwise means on a positively measured set, what I want doesn't hold, but you can restrict to that invariant set where it doesn't hold. So we may assume without loss of generality that in fact it doesn't hold everywhere. So we assume that for all x, there is a y behind them. Y behind x, f behind x, f behind x, such that the opposite inequality holds. So wx is less than or equal to wy. Now what I want to do is I want to pick such a y for each x. And to do this in a Borel fashion, I use Luzin-Novikov again. So by Luzin-Novikov uniformization, we can pick such a y in a Borel fashion. Well, there is a Borel function. There is a Borel function g0 from x to x that maps each x to such a y. I have a picture of this.
Why don't you pick closest?
Well, there are infinitely many. I mean, it's not locally finite, right? It's million to one. By million, I mean. Okay, so this is the picture. So this is the picture of this function. Okay, so what happens is, so each x picks some lexicographically list or whatever y such that x is less than or equal to this, and then this guy picks some lexicographical listing behind it such that this is less than or equal, bigger than or equal to this. So these points get only bigger in weight; they only grow in weight, and note that they sort of live on the same end. Like there is one end connecting, so they live on this geodesic from the forward end to their own one single end, because everyone picks a point behind it. Okay. All right. So thus, let me state this. Thus, for each x, the weight only increases. So the weight of x is less than or equal to the weight of g of x, which is less than or equal to the weight of g square of x, and so on. Hence, each G0 orbit is W infinite. It has W infinite weight because the weights only increase and there are infinitely many guys. So hence each G0 orbit has infinite weight in it. So by the exercise, so by exercise 3, the G0, the orbit equivalence relation of G0, the orbit equivalence relation EG0 is nowhere smooth. And clearly it's amenable because it's generated by a single function. And amenable. And amenable because it's given by a single function. Okay. So we built one amenable equivalence relation. Now the goal is to build another one that is orthogonal to it, independent from it, and use a cool result of Carrier and Gis that says that if you have two independent equivalence relations in a certain way, with a certain non-triviality condition, sitting inside a big equivalence relation, then this big equivalence relation is non-amenable. But ours is amenable, so that would give a contradiction. So now let's build another function. So furthermore, maybe, so also by losing Novikov, we can define a function. There is a Borel function G1 from x to x, taking each x to if such a thing exists, and if it doesn't exist, we just leave x alone. So to just an immediate preimage. So for instance, this x would take it to an immediate preimage, like here or here, that is different from where G0 chose to go. So G0 goes in some direction, we don't want that direction, but we choose something else in another direction. Okay, so taking x to y in the preimage of x, f preimage of x, such that y and G0 go in different direction. That I express this by saying that y and G0 x are in different connected. This is true. The paths from such that the paths from x to y and x to G0 only overlap at x.
What if there's only one?
Oh, maybe I say path from x to G0 doesn't contain y, such that the path from x to G0, this is the easy way to say it, doesn't go through y. If such a y exists, maybe that's what you were asking.
G0 or
G0 of x. G0 is the previous function. I'm defining G1.
There can only be one predecessor for some.
Right. So that's if such a y exists. Otherwise, just leave x alone. Wise map x to x. So if there's only one predecessor, then we don't do anything. Okay. So now note again that f is not essentially two-ended, and therefore, so since f is not essentially two-ended, whatever this essentially means, that means you can't reduce to a complete section where it is essentially two-ended. There will be points the x with two predecessors, with f inverse x bigger than or equal to 2. The orbit equivalence relation, the orbit equivalence relation of the orbit equivalence relation of this G1 is at least non-trivial. It has a non-trivial class, has a non-trivial, like non-singleton class in each E class, in each F component or E class. Okay, that's all I want from G1. So I want G1 to be non-trivial in each class, and I want G0 to be nowhere smooth. I mean, and both are amenable. Okay, so EG1 is also amenable. Okay, now what I will show is using this Pedalball lemma. I will show that these two equivalence relations are necessarily independent from each other. There's this notion of independence. I won't even define it. I will just talk about functions. So these functions are independent from each other, and therefore, by the following Carrier-Gis result, we get a contradiction to the amenability of E. So by our Pedalball lemma, applied to for equivalence relation for C-bears, not C-bears actually, for equivalence relation, applied E G0 and E G1, we get that EG0 and EG1 are freely independent. And if you only understand intuitively what that could possibly mean, if you know like when group elements are freely independent from each other, so or actions of transformations are independent from each other. Okay, so these are freely independent, and then we apply Carrier-Gis. Dependent, so which contradicts amenability, which contradicts the amenability of the big E by the following. So I'll just copy paste the Carrier-Gis result and read it. I really like it. It's maybe the only tool in the MCP setting before my work with Robin and my work with Ronnie and Greg that implies non-amenability of something. So the theorem is the following, that so E is a C-bear like we have, and assume that we have two sub-equivalence relations that are so F0 and F1 that are independent, which means that E contains their free product. So because they're freely independent, E contains their free product. Okay. Now we assume from F0, which corresponds to EG0, that it is nowhere smooth, which we proved, and we assume from F1 that almost every E class contains a non-trivial F1 class, which we proved. The conclusion is that then E is not amenable; it's nowhere amenable. But our assumption is literally that E is given by a function, so it is amenable. That's the contradiction. Okay, so now all I have to prove is, or show you, I'm not going to prove it. Proof is one paragraph, but it's a really annoying one paragraph. I'm going to prove state the Pedalball lemma. So the proof requires. So now what's left is to state the Pedalball lemma. So Pedalball lemma for equivalence relations. This is the more general version of Pedalball lemma, but that's a bit annoying to state because I need to then define what independence of equivalence relations is. It's more crisp to state it for permutations. So although we need the more general Pedalball lemma, Pedalball lemma for equivalence relations, I will only state it for permutations for simplicity. You can maybe guess the equivalence relation version. Okay, so what's the Pedalball lemma? For permutations. And Tserunyan problem. Okay. This is a very abstract lemma about an abstract tree. No descriptive set theory, okay? So like if you were sleeping before this, you can wake up just for this short moment. Okay, I see waking up people. So so that because it's like completely abstract, let T be a tree. Let T be even maybe uncountable, who knows, tree on a vertex set V. Let sigma be a set of permutations of V. I'm not saying set of three automorphisms or anything like that, just permutations of V, blind mixing up vertices, okay? Such that, oh, and let's start with let C plus be a distinguished end of T, some fixed end of T, be distinguished by nothing, just we fixed it, distinguished end of T. Let sigma V be such that for every V, so for every V, first let me copy paste the picture and then, okay. So my marching student, former student Matt says, can you stop writing nonsense and draw a picture? So before I write nonsense, I want the picture to be there. So this is my tree T. So this is the tree T. This is the distinguished end. And now I'm going to tell you what these permutations satisfy, such that, so for all V, I have, so condition 1 is that V, so this sigma, every permutation sigma maps V to behind V. Okay, so V belongs to, V belongs to sort of the opposite direction to the end, to the distinguished end. So V belongs to sigma V, the geodesic from sigma V to the distinguished end. Okay, for all sigma in sigma. And then 2 is that, so for 2 different permutations, sigma and tau, they have to go in different directions. Not immediately, but eventually. So, you know, so V is mapped by sigma to here. It can't map by tau to say here because it would go through it. It basically has to be incompatible. So I express this by saying that V does not belong to the line from sigma V to tau V. Okay, so does not belong to the line from sigma. I guess sigma is in blue here. Sigma V and tau V.
So they have to stay the same for this one. They can't
No, they can stand. They can immediately split.
So it wouldn't be,
No, they can immediately split. How do we express this?
Or like tau of it does not belong to the one between V and sigma V. No, this is what we could do.
What?
Tau of it does not belong to the line between V and sigma V. And it still goes behind. And this is the thing that you had before.
Okay. Yes. Okay. But I'm thinking maybe we actually do need. Sorry, can I cheat for a second? Where is this ping pong thing? See, you at least see that the paper exists. Okay, this is a strange condition. Sigma belongs to this for all distinct speed. What does that mean? Oh no, that means they can't go in the same direction. That's right. Sorry, I was wrong. No, this is not the type. So I was wrong by negation. It's the opposite of what I said. The picture is correct. So no, the picture is also incorrect, I guess. So
they split right away. This is what this is saying.
yeah, they split right away. So okay. So I was confused utterly. All right. So then tau v is this, and maybe tau v squared is this. Okay, they split right away. That's right. Okay, so they split right away, like we had happening in the theorem above, in the proof above. So for all sigma tau, sigma. Okay, so these are the two conditions, and so we think of this as like playing paddleball with this like paddle and an elastic line sticking out of it with a ball, so you keep kicking. So the player is here and it kicks here and then it kicks here and then it kicks here in that direction.
So here tau can actually go towards the end, and this is okay.
Yes, and yeah, that's totally okay. So for equivalence relations, I just want each equivalence for different equivalence relations, each class to sit on a different end. The class is a V to sit on the different end. That's what the correct generalization of this would be. Okay, then sigma freely generates the free group. And it's a free group which then naturally acts, extends the action to the group generated by it, whose action on D is free. So as many a sentence maximizing the number of free. Okay, so that's the conclusion, and this is what we need to feed to Carrier-Gis. So we apply this general version of this lemma to these two equivalence relations, then feed it to Carrier-Gis, which spits non-amenability, and that's a contradiction. Okay, so so I don't know, I don't have any more time. But if you give me 2 more minutes, I can explain what, like the end selection, to just like basically what started this project and which ends are selected. Do I have the 2 minutes? Okay, so this is my favorite part of the project, and I didn't get to say it. So which ends are selected? So we know that there is this end selection. Maybe this part I'll copy paste and just talk over it. So okay, so we know that if you have a treeable equivalence, a tree and an amenable equivalence relation F sitting in this treeable equivalence relation, then we know that each F class selects 1 or 2 ends. somehow magically. And the proof of end selection is done by using this, you remember when I defined amenability, I said that amenability means each class has this invariant mean, like this invariant and finitely additive measure. So basically you prove end selection by chasing where the measure goes. And like the measure turns out, like, maximal value of the measure goes to either all concentrates at one end or splits in between two ends. That's what happens. But a priori, when I give you a treeing and an equivalence relation F, you look at there is, how do you tell which ends are going to be selected? This invariant mean is like some abstract thing whose existence is proven using like crazy alpha filters. So we don't see it. But first thing with Robin was we realized that at least in PMP, it's very easy to see which ends are selected. And this is what started the project. So here is the theorem. So the first one is an observation. It has a 1-paragraph proof. I don't know if people observed it without us. I'm sure that someone will. So I don't want to claim part A for us, but part B is what we really proved afterwards. So fix an F class D. So let's say maybe I'll write like let E be treeable, MCP, nowhere dense, nowhere smooth, C bear, with treeing T, and let F be amenable subrelation. Be amenable. Okay, that's the setup. Now fix a D class, fix an F class D. So this is inside a big T, like big component, T component C, and we have one D class fixed. Now I want to see which ends are selected by this one F class. See, there are points here that are not red. That means they're not in D. They're not in the F class. Okay, so I want to see which ends are selected. And in PMP, when T is PMP, it's very easy. You take the convex hull of this of the class, so you add more points, and you get a new tree. Okay, for this class. Turns out this tree that you get in the convex hull has at most 2 ends. So guess which ends are selected? Those ends, right? So this is the part A, that this convex hull of each F class in fact has at most 2 ends in the PMP setting, and that's why these 2 ends are selected. These are the selected ends. So you can look at the tree, look at the F class, and tell exactly which ends are selected. In the measure class preserving case, it's more complicated. It's fast, so maybe you want to TD has this tree, this convex hull has less than or equal to 2 vanishing ends, but that's not true. It's possible that in fact all ends of T are non-vanishing, okay? But which one are chosen by the F class? So it turns out that this convex hull TD has at most 2 non-vanishing ends witnessed by the vertices in the class D. So you take the lim sup of the weights along the F class, and this lim sup has to be positive. That happens only for at most 2 ends, and those are the ends that are selected. So again, looking at the tree with the cocycle, you can tell exactly which of the less than or equal to 2 ends are selected. And this structural theorem has 5 consequences, and answered a couple of questions that I guess I don't get to talk about, but I'm happy to discuss it afterwards. Okay, thanks.
Questions for me?
If we go back to the theorem, Adam's theorem
For PMP,
no, for MCP.
or MCP, or at that previous lecture.
This perfect thing. So you said that there's a non-empty G delta with no isolated points. So I think it's still true that there's a perfect set of these.
But it's not a closed subset of the space of ends.
It contains a perfect set.
Okay, so you're saving my terminology from last time.
Perfectly many.
Yeah, so since it's Polish and perfect, it's okay to say there are perfectly many. Yeah, I guess saying that something is perfectly many doesn't claim it is a closed set. The claim is it contains a.
Yeah, there's a compact set. Which is
Yeah,
perfect.
yeah, yeah. Yeah, but this is not compact. Maybe I don't know. Yeah. Okay.
Can you go to the key lemma?
The core lemma, yeah.
Can you give a heuristic for this technical analysis? Why is this enough to look at this number?
Then you only look at the points that are dominating, and then you show it actually has to go to 0. It's first you prove that it is vanishing along that set, these dominating points, and then that's not too hard. And then after that, you sort of conclude that it actually forces the other points to also be go to 0. Yeah, otherwise other points would be dominating, but they are something like that. Yeah.
So in this the permutation lemma,
Yeah.
the most important permutations are actually surjective.
Yeah, here they are surjective. That's why I say we need the equivalence relation.
The function g0 is not surjective.
That's right. So that's why we have the lemma is actually for a set of equivalence relations on V. It's not for a set of functions. The general lemma for equivalence relations is for, you're given a set, curly E of equivalence relation on V, such that each equivalence relation chooses a set of backends, and then it promises that its classes are going to live on this set of backends. And the set of backends are different for different equivalence relations. It's like different tennis players on that side. Let's say maybe one equivalence relation has 3 tennis players, the other one has 4 tennis players, like these are the ends. And the point is that each V, like the class of each V, is this the ball. So the ball is only thrown by each team to their own ends, towards their own ends. So it's a different game. So it's not a pedal ball, I guess. It's something else in my mind, but it looks similar to pedal ball. Yeah. But yeah, that's right. You can't apply the permutations version inside the proof for many reasons, because also G1 is not even injected. G1 is not injected, right? It sometimes takes X to X. Yeah, so, yeah. That was the question. If there are no other questions, I want to just say that there were many questions like, to me, where should I read the background on this? So the background on equivalence relations should be read. Well, there's a very nice survey by Kekris. So Kekris has a survey. Kekris has a survey on C-bears. But I learned all of this stuff, this ends and so on, from also JKL that I mentioned before, Jackson, Kekris, Level. And this is the sort of the main source. And maybe I'll show you how attached I am to that paper. So this is in the, this is in the Munich airport, if you care. Yeah, so go there, I recommend.
Okay, let's thank Anush again for the 2 very nice.
The poster to put, please do it as soon as possible. The poster is on this top thing.
So I see your record. What is the normal mechanic? You just think for all